Good morning, everyone. Thank you for joining us for another edition of Power Hour. Today, we're going to be covering transformer loss compensation. And I'm joined by Brian Geringer, who is an expert on everything power. Go ahead, Brian.
Hi, everybody. As Johanna said, we're going to talk this morning about transformer loss compensation and see how far we get. Okay, so some of the topics I thought we might use to concentrate on are, we'll talk about what constitutes transformer losses. I will introduce an equivalent schematic diagram for a real transformer, which facilitates circuit analysis. I'm sure everybody's going to love the numbers, number crunching that we're going to be doing. We'll focus on two performance tests, the open circuit test and the short circuit test, which reveal the characteristics of the transformer, which permit you to do loss compensation in the field, assuming that you have a meter that performs loss compensation. I will sum up the nameplate ratings that are generally published with transformers and how they're used to do compensation. Near the end, we're going to distinguish the difference between measuring losses, which are, maybe interesting as far as they go, and compensating for them, which is the real purpose of the presentation, that you can actually read the watts and bars and energy at one point on one side of the transformer, even though the meter is connected on the opposite side of the transformer. And I'll show you an example of, how to make those settings in the meter so that it reads the desired values for watts, bars, and energy. So types of losses. There are a number of losses that make up transformer losses, what we would talk of as a general category. Certainly there are I²R losses that are dependent on the windings, eddy currents, which are core losses, hysteresis, and flux losses, which are all characteristic of the core. Temperature usually plays a role in the winding losses, and stray losses, which is also a factor of the windings. So just to begin from a point that everybody has a common frame of reference, I thought we'd start with the ideal transformer that everybody usually thinks about. This is what's normally taught in school, and it has a number of properties that make it lend itself to circuit analysis. So we start with the fact that the power into an ideal transformer is equal to the power out of it. In the diagram I have here, I'm showing subscript S as the source, subscript L as the load. So power, the source going into the transformer, is equal to the power delivered to the load. Expanding that into voltage and current vectors, you would say that the voltage on the source side times the current on the source side equals the voltage times the current on the load side. There will be a turns ratio, which develops the voltage from the source voltage to the load voltage. Usually, there are, of course, step-up transformers. Usually GSUs, generator step-up transformers, will boost the voltage from maybe 35 kV up to transmission levels. But most of the utilities who are doing loss compensation are receiving power from a transmission utility, and they may have, let's say, their meter on the low voltage side. That's the example we're going to do today. So, maybe on the primary side you've got 69 kV, and on the low side you've got 12,470. That's the sort of example we're going to give today. Of course, the relationship to the turns ratio of the current is the reciprocal of the relationship of the voltage. So high voltage, low current, low voltage, high current. And as far as circuit analysis is concerned, it's very helpful to be able to transpose the impedance on one side of the transformer into the effective impedance that is seen by the other side of the transformer. And we're going to use that as we explore the the different performance tests that we do today. So, in practice, we'd have a very short presentation if this wasn't the case. We recognize that the power fed into a transformer is not equal to the power that we can get out of the transformer, and that the difference in power, the delta P, the source minus the load, we call the losses. The losses are not a single feature, as we already talked about where they derive from, but they are the same whether you're going up or down. So if I have a meter on the low voltage side of the transformer, and I would like the meter to read the amount of power that's being delivered on the high side of the transformer, let's say I've got a 12470 low side and a 69 kV high side, and the transmission utility is delivering to the transformer, it might be of interest to know what power they're delivering to me. But the CTs and PTs are going to be much less expensive if I put them on the low side, on the 12470 side of the transformer, so it's very likely that's where the meter would be. So you can equally well say that the source power is equal to the load power plus the losses, or you could say the load power is equal to the source power minus the losses. The losses for any given amount of voltage and current are going to be the same. It's really just a question of whether the meter is on one side or the other, and whether you're interested in the opposite side or the same side that the meter is mounted on. So the losses in the transformer are generally done in aggregate. The nameplate values that you're given when you buy a transformer are done in three-phase levels. They are separated into copper losses and iron losses. The copper losses are proportional, are generally properties of the windings, and they vary along with the amount of current or your load during the course of the day. As you go from off-peak to on-peak, your copper losses will increase. On the other hand, the iron losses are proportional to the voltage at which the transformer is operating. And of course, the voltage does vary to a certain extent with load, but for the most part, if a transformer is rated for 69 kV into it, it's going to be operating pretty close to 69 kV all the time. So you don't see as much variation over the course of the range of load from off-peak to on-peak regarding iron losses. The other thing that I wanted to point out is that you'll notice that the impedance elements that we show for the winding losses and the core losses are not purely resistive. We talk about I squared R, but we really mean I squared Z, for impedance. But because they're not purely resistive, we have some concern about reactive power. So your reactive power is going to, your losses due to reactive power are going to be changing at a different and independent rate from the watt losses. So we're basically dealing in two dimensions. We have to deal with iron and copper watt losses and iron and copper var losses. So four parameters that we're interested in. Now, because copper losses are also called load losses or winding losses, and because iron losses are also called core losses, the terminology can get very cumbersome, and you have to keep track when you're doing the math of what is being presented and what you're calculating. The other thing that I wanted to point out at this point is that since we're going to be doing a little bit of circuit analysis, I'm doing everything here with a single-phase diagram, but we will have to make a transposition at the end between single-phase and three-phase because the nameplate ratings of the transformer are all given in terms of three-phase values. And usually the voltage in a single phase, it's easier to look at the line to neutral voltage. On a three-phase transformer, most of the values and the ratings are given in phase-to-phase units. So on the one hand, there's a root-of-3 multiplier to deal with. On the other hand, there's a divide by 3 factor that we have to be concerned with. These are the reasons why people generally, I find, have the impression that loss compensation is difficult. It's more a function of terminology and keeping things straight than it is the underlying theory that goes into the losses and the compensation for those losses. I also wanted to point out in this slide that because the impedance elements are both real and reactive, there is a factor that is dependent on frequency. Now, you can build a transformer to operate at 60 hertz, and you can build a transformer to operate at 50 hertz. Sometimes it's the same transformer with different nameplate ratings. Fact of the matter is, the frequency is so tightly regulated, you don't really have to worry about losses due to frequency, except when you have high harmonic content, particularly your load may have high harmonic content, and then what you're dealing with is every discrete individual harmonic component has a different impedance characteristic depending on the contribution of that harmonic component. So if you have a frequency that's 3 times the fundamental frequency, the reactivity is going to be much different. So obviously with high harmonic content, you increase losses and you also increase temperature. When you increase temperature on a transformer, you derate its service life. There is also a temperature component to losses, but by and large, most transformers are either low enough power that they can operate at ambient temperature regardless of the rise and fall of the seasons, or they have fins on distribution transformers or fans on liquid-cooled transmission transformers. So to the extent that temperature-related losses are a factor, the temperature is typically controlled to minimize the impact of the temperature on the losses. I thought I'd mention a few benchmarks just to put us in, rough, rate of comparison. So to start with, coil losses or copper losses usually range from about 1.5 to 2% of the total load. Core losses, iron losses, make up about half of 1% of the load. We often hear about people talking about the losses being, roughly 2% of the load that you're concerned about. The fact that the iron losses are relatively constant over the entire load range and the winding losses increase with increasing load means that the loss profile, the percent efficiency, is not linear, and there is sort of what we might call a sweet spot where the losses run about 2% of the total load. Now, putting the percentage in perspective, why are we concerned about something that's as small as 2%? Well, if your meter is rated at 0.2% or 0.1% accuracy, and you've got 2% losses, it's a whole order of magnitude difference between the accuracy of the meter and the contribution of the losses, so it's fairly important. Another aspect of the proportionality is since we aggregate the losses among the 3 phases, and we calculate the losses based on the assumption of a relatively balanced load. There is some deviation in the calculation of the losses over abnormal conditions of balance and loading. So people wonder if my accuracy, if my loss calculation, let's say I'm taking the losses and I'm off by 2 or 3 or 5 or 10%, what good is it to report the losses? Well, remember that 2 or 5 or 10% accuracy in measuring the losses is 2 or 5 or 10% of the 2% contribution to the total load. So even if your calculation of the total losses is off by a fairly large number like 5%, that's still 5% of 2%, which makes it worth calculating. You can't just assume that the accuracy of the losses translates into the accuracy of the measurement of power. And that's the important part, is the measurement of power on the opposite side of the transformer from where the meter is connected. So everybody has to start with the nameplate that is provided by the manufacturer of the transformer. The nameplate characterizes the performance of the transformer based on tests that are performed after the transformer's been manufactured and before it ships. So, you know, the manufacturer may choose, depending on the application of the transformer he intends, to use a heavier gauge wire or a smaller gauge wire. He might choose to use a larger gauge wire on the low voltage side because it carries more current than on the high voltage side. The number of turns determines the impedance of the line. And their spacing on the core has something to do with the inductance and the capacitance of adjacent windings. So, you know, the manufacturer has a certain loss characteristic in mind when he manufactures the transformer. That's built into the design of the transformer, but once it's done, they have to perform these performance tests in order to give you a number that's accurate enough that you can compensate for. So the two tests that we're concerned about are the open circuit test, which is also called the no-load test. It's performed by injecting the rated voltage on the low side of the transformer with the high side open. Okay. 12,470 is a voltage that a manufacturer of transformers can generally develop. He can inject it into the low side of the transformer with the terminals of the high side open, and the amount of current passing through the windings from that injected voltage gives you some idea of the iron losses, the core losses of the transformer. I'll talk a little bit more about the short circuit test after we examine the detail of the no-load test. So here's my equivalent diagram again. This is a real transformer. What I've done is I've removed the source and I've removed the load. So all we're looking here is the 4 terminals of the transformer. And I've put a source on the low voltage side. Now, the source can inject 7,200 volts. Remember, for simplicity, we're going to stick with the 69 kV primary to 7,200 volt secondary. Remember, I said it was 12,470. 12,470 divided by the root of 3 is 7,200 volts lined to neutral. So we're going to have approximately 40 kV on the primary side, 7,200 volts on the secondary side as a result of injecting 7,200 volts on the low side with the high side terminals open. So what we can see from this is that you can measure the amount of current that is being drawn by the circuit, and that excitation current is one of the nameplate values that's reported by the transformer. The important part of the schematic drawings that I'm going to show you in the next 4 or 5 slides is not so much that you know, let's say, that the power P4 in this diagram is 3.2 VA. That's not the important part. The important part is when I compare the power 3.2 VA of the windings on the low side of the transformer to the 12.7 kVA, 12,700 VA of the iron losses. The significance is that the amount of power drawn through the iron losses is so much greater than the amount of power lost in the windings that under these open circuit conditions, you can ignore the winding contribution, the series component. You can ignore the series component as round-off error compared to the contribution of the iron losses. Now, this slide was intended to show you the real transformer without a source, with the primary side open and with a voltage injected on the low side. But for circuit analysis, it might even be easier to envision this if I were to transpose the effective impedance of the iron losses on the primary side across the ideal transformer and show you what the contribution is. So if I'm injecting 7,200 volts and I've got 125 k ohms on the primary side, I can transpose that onto the secondary side, and that works out to 4,092 ohms. Now, these numbers, the ones that I have highlighted in red, the 1 ohm Z4 and the transposed 125 k ohms, these are numbers that I reverse engineered from the example that was given in the reference guide that we're using, which is the ANSI IEEE standard C12.19 standard. And they go through the entire process. Now, nobody measures the ohms, and nobody says it's this many ohms resistive and this many ohms reactive. But, you know, just working in ballpark numbers, this gives you a sense of what's a high impedance, what's a low impedance, how much current is flowing through the circuit, and how much power is absorbed by that component. The power absorbed by that component represents either iron or copper losses. So this is how we determine the ratings and what we do with them once we have them. So again, on a per phase basis, what you're seeing here is about 12,700 VA dropped in iron losses. You're seeing about 3.2 VA dropped in the winding losses. So we're going to ignore the contribution of the winding losses and say that the result of the open circuit test reveals the iron losses. The short circuit test does exactly the opposite. So the short circuit test is intended, you might imply from the last test, that it's intended to isolate the iron losses from the copper losses and reveal the copper losses in a situation where the iron losses are so small that they can be ignored as round-off error. So the way we do that is we inject only as much voltage into the high voltage side, so much less voltage than the 69 kV that the transformer is rated at, but only so much voltage as is necessary to produce the rated full load current with the low side terminals shorted together. So as you can see, I've reintroduced the source voltage. My source voltage, it turns out, I can develop the rated current on both the high side and the low side. I can develop the rated current by injecting 2,000 volts into the high side windings. Again, I reverse engineered that from the losses in the IEEE standard to show what we've got here. You see how the low side, I've replaced the load with a short circuit. So the voltage across the short circuit is obviously 0. Since I'm injecting the rated current, how did I get the rated current? Well, the rated current is the rated voltage. This is a 10 MVA transformer. So 10 MVA divided by the 69 kV, well, let's say 69 kV divided by the root of 3 because I'm working on a per phase basis. So basically 40,000 volts. I've got, so 10 divided by 3 MVA is 3 MVA divided by 40,000 volts gives me 83 amps. That's my primary current. And when I pass 83 amps on the primary side of the ideal component of the transformer, what I get is 463 amps through the short circuit. Again, the impedance is a function of the wire gauge and the windings and the nature of the core. So the figures that I used in the open circuit test are still good. The impedance figures are still good for the short circuit test. So the impedance of the parallel component is still 125 k ohms, and the windings, I just took equal values in terms of impedance that develop different amounts of power drop depending on the amount of current that's passing through them. So again, we eliminate the ideal transformer by transposing the effective impedance of the opposite side of the transformer across the transformer. So that comes out to 223.4 thousand VA loss in the load side windings and 7.3 thousand VA loss in the high side windings, but only 57 VA in the iron windings. That's just a result of basically Ohm's law. So you can see from the amount of current that's passing through the 125 k ohms, your power dropped through the core is going to be very small. Of course, we're only injecting 2,000 volts on a transformer that's rated for 4,000 volts on the input side. So you would expect under these circumstances that the iron losses might be much smaller. And this reveals the copper losses, which are the primary side losses plus the secondary side losses. So 7.3 plus 223 is 230,000 VA are my copper losses. So the nameplate captures these values that we've been talking about through the circuit analysis. These are the exact ratings that are given in the example in the ANSI C12.19 standard. So a 10 MVA transformer that was designed for 69 kV on the primary side and 12,470 phase-to-phase on the secondary side. When we do the open circuit test, they generally have a watt meter in line with the source. So they take a reading off the watt meter and they calculate the percent impedance and the percent excitation. The excitation current is the amount of current drawn during the open circuit test divided by the rated current, and the percent impedance is the voltage that 2,757 volts divided by the rated 40,000 volts. So I get 6.92% impedance and 0.38% excitation current. And I have the watt losses for both the iron and the copper components, the winding and the core values. Now these are the only values that you typically get with the transformer, and it's not obvious exactly how the meter uses those things to compensate for the losses given in the transformer, so that's where our example is going to come from. So here's what you do with the figures that are given to you from the nameplate. Let's start with the iron losses, which are, or rather the watt losses, not necessarily iron, both iron and copper, but the watt losses are given by the nameplate. So I've got 9,878 watts, 9.8 kilowatts of iron losses, and I've got 41 kilowatts of copper losses at full scale. How do I calculate the VA losses? Well, the VA losses are the VA, the full rated VA of the transformer, times the percent excitation for iron losses. Or if I was looking at copper losses, it would be the rated kVA times the percent impedance. So in the one case, it's 10 10,000 kVA times 0.3%, 0.38%, which is 38 kVA. And in the case of the copper losses, winding losses is 10,000 kVA times 6.92%. So that's 692 kVA. This gives us two sides of the power triangle. So we're able to derive the watt losses, the VAR losses, by solving for the perpendicular component, which is the done just by applying Pythagorean theorem to the VA losses and the watt losses. Now, iron losses are given by this procedure at the rated voltage, and copper losses are given at full scale. So these are the amount of losses that you see. And at full scale, at the rated voltage, you notice that the copper losses, the winding losses, are significantly greater than the core losses. But of course, as the load varies off peak, you may get to a point where the iron losses are greater than the load losses. So everything is dependent on how much load is being carried by the transformer. So coming back to the C12.19 standard, there's a section where the agreed upon equations for delivered or received loss compensation is calculated. The reason that I mention this is because it is a well understood, mature technology. It doesn't change. And this is the equation that's used by the meter to measure the voltage and current on one side of the transformer, either add the losses or subtract the losses, and come up with the watts and bars on the opposite side of the transformer. Now, the way I express this in my own application note is to show it as an equation where the load losses times the measured current divided by the maximum current squared, plus the iron losses, which is the no load losses times the voltage measured over the reference voltage squared, equals the watt losses, the total watt losses. And the VAR losses equals the load losses, the VAR losses, times the same factor, the measured current over the maximum rated current squared, plus the iron losses, which are the calculated value from the Pythagorean theorem, times the fraction of the voltage relative to the rated voltage squared twice. So it's squared and then it's squared again 4 times an exponent of 4. Now we're going to play a little bit with these equations by expanding the square factor. You can say the measured current over the measured current squared over the maximum rated current squared is equal to the number that you multiply by the load losses, either for watts or bars, and the measured voltage squared over the rated voltage squared times the iron losses combined to form the total watt losses. And if you take the ratio of the measured voltage to the 4th power divided by the rated voltage to the 4th power and multiply that by the no load VAR losses and add that to the copper VAR losses, you get the quantity of losses in watts and bars. Now, I'm going to take this one step further. I'm doing this one step at a time so that we don't lose anybody by skipping steps. You notice that the figure in the numerator is the voltage and current measured in real time by the meter. So this is a value that the meter contributes that you don't get from the nameplate. It goes up, it goes down, and the only way to know what that figure is by the meter measuring it. But the figure for the load losses and the no load losses, the copper and iron losses in both the watts and the bars, are all constants. Those are values that are either on the nameplate or derived from figures given to you by the nameplate. And the maximum rated current and the nominal voltage are also constant over, it's the value that the transformer is rated for, so they don't change. So what I'm going to do in the next step is I'm going to group all of the constants into a coefficient, which leaves the measured values as variables. So I have a coefficient times a variable. The variable is measured in real time by the meter, and the coefficient is a constant that doesn't change regardless of anything. So when you do that, I may as well call the losses divided by the ratings constants. I may as well give them a simpler variable, call them A, B, C, and D, just to make the equation look a little bit simpler. And these will be the settings that you have to make in the meter so that when the meter measures the current and voltage, it multiplies the current squared times the A factor, and it multiplies the voltage squared times the B factor, and the sum of those two gives me the watt losses. And again, for the VAR losses, it's the current squared times C and the voltage to the fourth power times D. If A, B, C, and D don't change, you must calculate those and enter them into the meter because the meter has no way of knowing what the ratings on your transformer are. So, summing up, if the compensated power is equal to the uncompensated power plus the losses, and the losses are equal to the A, B, C, and D coefficients times the respective current and voltage, either squared or raised to the fourth power, then we can say that the compensated power is equal to the uncompensated power plus the A, B, C, and D factors times the voltage and current that are measured in real time. Now that's what the meter actually does. So I mentioned earlier in the presentation that knowing the losses may be, of some curiosity, maybe of some interest in the abstract, but it doesn't do anything for you. What you're really concerned about is having a meter that resides on CTs and PTs that are located, let's say, on the low voltage side of the transformer, which doesn't read the power on the low side. It reads the power on the high side with the compensating factors added into it. Now, if I had the meter on the high side and I wanted to know what was the power on the low side, then I would simply subtract the A, B, C, and D factors from the uncompensated watts and bars. The meter normally measures watts and bars, so the P uncompensated and the Q uncompensated are already in the meter. What it has to do the compensation is to measure the current and voltage, square it, or square it twice, and then multiply by the corresponding A, B, C, and D factors. So, a couple techniques. Remember, I said that the theory isn't so complicated, but the application gets cumbersome because there's so many terms that we have to keep straight. Okay, so we know from the previous example. This is the short circuit test, that the watt losses, we know from the nameplate that the watt losses are 41,427 watts. But if I'm calculating the A factor, and I say the A factor is equal to the losses over the full load current, but the full load current on one side is 83 amps and on the other side is 460 amps, which figure do I use as the denominator? Which value do I square and use as the denominator to calculate my A variable, my A coefficient? So remember, this is how you keep it straight. Remember, the ratio that we're interested in is the proportion of the full load current that the transformer is operating in. So it only has relevance as compared to the current that's being measured. Remember that I over I0 factor. That gives me the proportion of full rated load that I'm operating at. So what it comes down to is which side of the transformer is my meter on. If my meter is on the low side, then I use the low side current. If my meter is on the high side, then I want to use the high side current in calculating the A factor. That makes sense? So in either case, the way you calculate the amps, the full-scale rated amps, is to take the full-scale rating of the kVA rating of the transformer divided by the voltage rating, and that gives you the current. Obviously, low voltage side is going to have high current. High voltage side is going to have low current. Now, on the voltage, so for my B factor, this applies both to the B and to the D factor, we have the same question. Do I use the high voltage side or the low voltage side, the 69 kV or the 12470 kV? But we also have another factor. Do I use, when I'm calculating my B or my D coefficients, do I use the phase-to-phase voltage or do I use the phase-to-neutral voltage? Now that's important because if I am measuring the phase-to-phase voltage with the meter and I'm dividing by the phase-to-neutral voltage, you're going to get the wrong answer. So the trick, it's more of a convention for the meter than anything else. Whether you've got a delta-connected winding on the high or low side of the transformer or you have a Y-connected, delta or Y, the meter will always be able to determine the phase-to-phase voltage. On the other hand, if I've got a delta-connected primary or a delta-connected low side, I may not have a phase-to-neutral voltage. So what the meter typically does is it'll compare the measured phase-to-phase voltage with the rated phase-to-phase voltage. So when I calculate my B coefficient and my D coefficient, what I really want to use is the voltage on the same side of the transformer that the meter is mounted on. And I want to use the phase-to-phase voltage to make those calculations. Now, everything that applies to A in these two examples applies to C, and everything I've said that applies to B also applies to D. So we'll take the next step, the next logical step. So here's the premise. If the meter is connected on the low voltage side, where the CTs and PTs are going to be less expensive, and you're interested in knowing how much power is being delivered to the high side, your transmission utility is delivering the high side voltage, the high side power is being delivered to your transformer, and you own the transformer, but you place your CTs and PTs on the low side of it, and you want the meter to read how much power is being delivered to the transformer, you want to add the losses. So my A, B, C, and D coefficients are all four of them a positive. If I had the meter on the high side of the transformer and I wanted to read the power on the low side of the transformer, then the A factor, the B factor, the C factor, and the D factor would be negative. So bringing the numbers in from the values that we showed in the open circuit test and the short circuit test, we divide out the full load copper watt losses by the full load rated current, and we get an A factor of 0.1933. Dividing the iron losses, iron watt losses, by the rated voltage, since we're on the low voltage side, we're looking at 9,800 watts divided by 12,470 squared. Since the 12,470 is a large number and then we square it, it's no surprise that we're going to get a very small number for the B factor. My C factor is going to be the 690.7 kVARs that we calculated with the Pythagorean theorem, divided by the 463 amps secondary full-scale current squared is 3.2. And finally, the D factor is the calculated iron VAR losses divided by the rated voltage on the low side, squared and then squared again. So you can well imagine that 36,000 VARs divided by 12,000 to the fourth power is going to be a very small number. So, typically we'll see my B and D factors are usually pretty small. Anyway, what do I do with those values? Typically, the meter will make use of those values when they're entered as a setting. And if I enter those settings in the meter, it goes back to the equations that we talked about. This equation, the one on the bottom of this page. And it says I'm measuring the current. I'm going to multiply by the A factor. I'm measuring the voltage. I'm going to square it, measure and multiply by the B factor. I'm going to take that result, which are my losses. I'm going to add them to the watts that I measure anyway, because it's a watt meter. And I'll get the amount of watts that are being delivered to the high side of the transformer. And the same thing holds true for VARs. I take the VARs that I'm measuring anyway, and I add to that the square of the current times the C factor and the voltage to the fourth power times the D factor, and those are my VAR losses, and I add that to the measured VARs, and I get my my compensated VARs. And that is transformer loss compensation. Now, there are a couple of variations on this that I would want to introduce without actually doing the math, because I think at this point, with all of these numbers, I think people are starting to get a little weary of the depth of the math. But I wanted to mention that line losses are very much related to transformer losses. But in the case of line losses, what you're dealing with is a length of, let's say, distribution line or transmission line that's many miles long and has a certain amount of impedance in it. And basically, the difference between line losses and transformer losses is simply that there are no core losses in a line. You have watt losses and VAR losses, but you only have the A and the C factors times the current, because I've got watt losses that are I squared R, and I've got VAR losses that are I squared X, but I don't have any losses in my line that are related to the voltage. The losses in my lines don't have any contribution to iron coupling with an iron core. So the way you do line losses is you simply ignore the B and the D factor. You take the resistance and the reactance, which are properties of the line, and they're published, they're tested, end-to-end tests are usually performed by the protection department so that you can do distance protection. So they should be published values that you would have. And I simply make the A factor is equal to the resistance of the line, and the C factor is equal to the reactance of the line times the square of the current, and that gives me my line losses. Now, what makes that complicated is that sometimes, because the line is a certain gauge of wire, you may have different resistance depending on the size of the line, and you may have different amount of resistance per foot based on whether I've got a single conductor or if I've got three conductors ganged up on my line to carry the same amount of current across three conductors. I may have to do that math, but that all goes into calculating the A factor and the C factor in this loss compensation equation. So that's one variation on transformer loss compensation. There's one other variation on the theme that I wanted to touch on without going into great detail, and that is what happens when I've got What happens if I've got the CTs on one side of the transformer and the PTs on the other side of the transformer? Now that's interesting because in that case, your voltage is a function of the PT ratio times the turns ratio of the transformer, or your current divided by the turns ratio of the transformer. But the A and the B factors still exist. You simply have to use the side that they're on. So the A factor is dependent on which side your CTs are on, and the B factor is dependent on which side the VTs are on. And that will give you the resulting losses if you've got CTs on one side and PTs on the other. So that's the other variable that I wanted to introduce. We could go into great detail about both of those examples, the line losses and the case where the CTs and PTs are on different sides of the transformer. But I thought I'd leave that with theory and leave the math for maybe a later presentation. We also have an application note that goes into examples of each of those. And that application note can be downloaded from our website. So with that, I could open up the floor to questions. Pretty much concludes my prepared remarks. Presentation is available for download, so if you want to compare the figures that I calculated in my open circuit test and my short circuit test to the aggregated figures that come from the nameplate, you can do that. They're fairly typical and can be scaled up or down depending on the size of your transformer. So that's pretty much everything I've got.
Okay.
Thanks for your attention.
Well, this Power Hour will be available on our power.novatechautomation.com website, including our previous or old webinar recordings. With that, we'll finish it up. Thank you for joining us.